Hello and welcome to the part 7 of Hexagonal Multi-surface Pattern lesson in Grasshopper. In previous session we learned about surface construction, UV domains and primitive data mapping from Cartesian coordinate system to local UV domain of the surface. Today we put this knowledge to practice and map a hexagonal grid of points from our script to a surface. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. So that's where we left off, and let me remove the remnants of the previous lesson. The previous one was fully theoretical, so let me just delete all of this. And as you can see, my script is turned off temporarily. We did it in the beginning of the previous session. Basically, we did no changes to the script, so it's time to do it now. So select everything, middle mouse button click here, it's turned it on again, and start compiling. I will remind you, you can go into the description to this lesson and just download the script. So let's now use the knowledge we acquired from the previous lesson and map this hexagonal pattern on a surface. What we need to do that? Well, first of all, we need to construct a surface, right? I will do the temporary surface, just something to visualize how we actually do that. And the simplest way to construct the surface is construct the surface through points in Rhino. And I mentioned it before that the surfaces require curves, but the curves will be constructed automatically through the points. So I'll use this node. It's called node instrument in Rhino, which is called surface from 3 or 4 corner points. Click on this one. And with my grid snap turned on, I will just go in clockwise and construct the points 0, 1st, 2nd, and 3rd, 4 points. So let's do that. So let's go here. 1, 2, 3, and 4. We have ourselves a surface. Once again, it is a temporary surface. We then replace it with something more meaningful. So this surface is planar, but it is a surface. So we can try to map this on our surface. You already know what to do. First things first, we need to construct a bridge and toss this geometry to the Rhino, or as I said, bridge it to the Rhino. So to do that, you already know we need to go to the parameters, geometry, and pick the type of geometry you want to stream. That will be the surface. So bring it in, right click, set one surface, click on our surface. As you can see, right now it's bridged, right? Next, we need another node which called, I'll remind you, evaluate surface. So basically, it will ask for the points of our grid and the surface we want to map these values onto using the surface domain. We don't know what domain it is. Well, I can predict, but let's for now just take this node and put it to the end of our script. Then I need to construct a long wire which basically goes from the surface to the surface right there. Now to do it, I will just drag it a little bit down here, double click and use some pass-through node, like for example, I don't know, data, for example, just temporarily plug it in, double click, create a couple notches, one here, one there. Let me delete this. Select the notch, hold shift, click and drag, so it will be parallel to my grid, like this. Just keep moving, keep moving, keep moving, keep moving. All right, I like that. Now, this is my pattern. This is my surface. Let's connect. So point to point, that will be the UV representations, and the surface to the surface. Once again, you already know how this node works and why it works. Right from the get-go, we have a lot of additional information, which is our planes. We're not talking about the planes yet, so select the node, Ctrl-Q. I just disable it from the viewport, and I would like to specify what kind of a data we want to look at. And it gives me a lot of data: point, normal, directions, frames, which is planes. I need only points. I already showed you how to do it in the previous lesson. Click the pass-through node, this one, which is the point, and I'm specifying the type of data. The type of data is the point. I want to look only at the points, right? Now, before we continue, let me quickly go through our script and make sure that we are on the same page. So we have quite a few switches already. For example, we have an ability to construct additional weavings for our hexagons. I don't want them right now. So my switch of a geometry is set to hex only. I will keep it like this. Next, we have another one here, which defines the type of structure. Is it closed or opened? So basically, is it bite its tail or not? For now, we are talking about the opened surface, so we don't want to close it, right? So the structure type set opened, right? And in the beginning here, we have a really important switch, which defines the type of a hexagons. And we have 4 options: anisotropic flat top, anisotropic pointy top, isotropic flat top, and isotropic pointy top. I hope you remember why we have 4, but just very briefly, isotropic is the grid. Let me look at the pattern itself. So isotropic is the pattern which we weaved from isotropic grid. Basically, its size is 1 to 1, and the grid is normalized between 0 and 1. And because they have the same distances between the points, the hexagons themselves become to be skewed, because the hexagon, the actual aspect ratio of a hexagon, is anisotropic. Basically the square root of 3 difference between width and height. We are not using it right now. In isotropic mode, we just weave it as it is, as if it was a square. And trust me, it's a really good like set, and we're gonna specify the actual parameters and its actual ratio using the divisions now. As you're gonna see, I have, by the way, 2 additional rows. Let me put them back on to 0. And you're gonna see by changing the amount, changing the aspect ratio of the hexagons. And this is the nature of the isotropic pointy top or isotropic flat top, right? This is the mode number 1. The mode number 2, anisotropic, it's the same. It's still normalized between 0 and 1, but we have compensation, right? So for the flat top, the x component is the same as an isotropic grid, but the y component become to be bigger. How much bigger? On square root of 3. We've already figured out y in the previous lessons, so we put this additional compensation. This is x, this is y for the y component, so they automatically become the proper size. And you can see it's not a square, it's now a rectangle. And the pointy top is vice versa, right? Now the y component stays the same, but the x component is now the y component, this one, it stays the same, but the x component is now spread on square root of 3. Okay, so as you're going to see, we have this kind of 4 modes, right? Or 2 general modes and 2 like rotations, one of them flat top, another one pointy top. So we'll use the flat top as the beginning, and we will talk how to map this one first, because of course there will be differences between the 2 modes, right? So we actually already mapped it, and as you're gonna see, this is our surface. We already mapped our pattern, this pattern, on a surface, and you're gonna see some strangeness with it. Now, first of all, what do we actually want to get when we take our isotropic grid, right, of points on a surface? What kind of a behavior we want to expect? What do we want to expect? Well, I believe the most natural one is to expect that this grid actually stretches across the whole surface. Well, kind of logical, right? It will be a really good solution for this mode, but it's not doing it out of the box. On top of that, it's actually not on the surface. Only quarter of a pattern is on a surface. That's definitely an issue, but that's not all. If you look closer at the arrangement, let me actually go in and construct the polylines here, just temporarily. You will notice that it's supposed to be a flat top. It is a flat top, but here it's pointy top. What's going on? Now we have 3 problems. Let's tackle them one by one. Now, first of all, let's address the fact that it's pointy top instead of a flat top. Why? Because the orientation. Let's look at the domain of the surface. You already know how to do it. We will use the node called domain squared, this one. Remind you, it's in the primitive section here under the parameter main tab of a palette. Plug that in, use our panel, and check what's inside. And you're going to see that it gives us the Rhino automatically remapped geometric domain of the surface to a parametric one, and it decides that it's really good numbers, 0 to 10, 0 to 20, actually really very good. When it comes to the planar simple surfaces, the domains are pretty predictable. So 0 to 10 for U, 0 to 20 for V, 20 for V. Let's look at the surface. 0 to 20 is supposed to be the longest side, right? 0 to 20 and 0 to 10. This is V and this is U. All right, this one is X and Y. And I hope you remember in the previous lesson, I told you that we agree in computer graphics that when you map primitive data from Cartesian coordinate space, X value transfer to the U direction and Y value transfer to the V direction. And it does. But because this one is V and this one is U, it rotated basically. So the script works correctly, but the orientation is different because U and V are not on where you think they are. Now to really inspect that, and understand that, we're gonna select our surface and type dir in the command prompt of the Rhino. Hit enter. And you're gonna see the right arrow goes up. This is a U direction. And the green arrow goes right. This is our V direction. So it's flipped. Can we flip it back? Yes. Well, we are still under this command. Go here to the top and click swap UV. Click and hit enter. Now if you zoom in, oh, now it's in the proper direction. This, as you can see, U become to be 0 to 20. This is 0 to 20. V, 0 to 10. 0 to 10. So now it's properly oriented. Why it was originally oriented differently? Well, that's because when I constructed the point, I go clockwise. First point, second point, third and fourth. And the first direction is always U direction. So I actually manually defined this direction as a U direction. And this one was a V direction, right? Okay, so these are the, we understand what's going on. We fixed the directions. What's about the position? As you're going to see, only quarter of it is on the surface. Why it is the case? If you look at the nodes at the panel, you're going to see that our domain starts, or our mapping, our ruler for the surface, for parametric domain starts from 0. 0 to 20, 0 to 10. But our pattern, which is between 0 and 1, is centered. Why it is centered? It's centered because we manually bring it back to the center to negative X and negative Y on half a distance from our original 0 to 1 space to be able to rotate that, right? We did it a couple lessons ago, and you know that for rotation, this is our 2D rotation formulas. We rotate that around the global Cartesian coordinate space. So we basically need it to be in the center, and it is. But we never moved it back. So it's still on the center. It still have a positive values for points and negative values. So it has positive X and negative X, positive Y and negative Y. And because we have negative values, it actually goes outside of the surface, right? In our case, if you really want to stretch it, that's not a good idea, right? So we need to add half a distance back. How are we going to do it? Well, actually, literally, we will add half a distance back. We know that this is a normalized space. We literally normalize all the values. And because it was a half a distance and it was a 1, 0 to 1, we need to add how much? 0.5. Correct. Let's do that. Let's select everything up to this point, move it to the right. This is actually our original pattern here. Now, to remove the confusion, let me actually hide this one, and go to our original. That was the original grid, right? The one we weaved. So what we're gonna do, we'll deconstruct the points on components, add 0.5, and then construct the points back. So deconstruct the points, I'm using the quick callout. I hope you remember how to do that. Now we need to, when we deconstructed the point on components, we use expression, and we will add 0.5. So it will be X plus 0.5, and it will be X component, and the output will be X. Plug that in, and the same for the Y, right? So this is the Y component, right click, Y, that will be Y, all right? and the output will be y. I'm just organizing the variables so it will be easier for us to understand. So we change the components. Now what we need to do, construct a new points. So go in, construct point. Once again, I'm using quick callout x and y. Here it is. Now it's on from 0 to positive x and from 0 to positive y. Great. Let me hide this one. And this is the new, or it's basically the proper shift of our pattern. Now let's switch it. Let me actually delete this one. It's actually the visualization of the points of the connections. So we plug that into our script. We toss it through. Bam, 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 bam. Look here, and yes, now it is in the proper start. Let me go in and just set boolean true to just close my polylines. Once again, this is just a temporary visualization. Okay, so we solved two issues. But there is another one. It's not stretched. Why it's not stretched? Well, I guess you already know why. The domain of the actual ruler is from 0 to 20 and 0 to 10. 0 to 20 and 0 to 10. Our domain, 0 to 1 and 0 to 1, right? What we need to do? Well, there are two options for us. Option number one, take our points, and because the domain, check the domain, figure out what the size of domain, and then multiply on the proper scale factor, right? But it's kind of like meh solution. It basically gives us a lot of headache. But we have a simpler approach. Remember, I said that you can, it's under the user control to change the ruler, change the parametric domain of the surface. Because as I said from the previous lesson, you can measure the surface the way you want. You can measure that with bananas or with sticks or with whatever range of numbers you want. It's up to you. It's up to you how you map it. And what we can do is, instead of a 0 to 20 and 0 to 10, we want to stretch, right? So it will stretch no matter what. We will change this to 0 to 1 and 0 to 1. Why 0 to 1? Because this is a grid which has the values between 0 and 1. We literally, from the beginning, right in the beginning, x in the power of -1, we normalize that, right? Or 1 divided by x, the same thing. All the values between 0 and 1. So if the u direction and the y direction will be mapped from 0 to 1, it automatically stretches everything, right? How are we going to do that? Well, there are two options. One through the Rhinoceros and another one through the Grasshopper. Now, even though the Grasshopper works under the same kernel, Open NURBS and the Rhino common, the actual capabilities of the system of the Rhino itself is much bigger. Rhino use only partially some of the functions. And when it comes to reparameterizations, the only thing Grasshopper can do is reparameterize to 0 to 1. Whatever domain you have, it can immediately reparameterize it to 0 to 1. If you want different numbers, not like 0 to 1, but 0 to x and 0 to y, then you need to use the Rhino here. We will do it later. For now, we don't need that. What we need is a normalization. How are we going to do it in Grasshopper? Very simply, select the node which contains your geometry, right-click, and you're going to see that a part of the stuff you already know, graph, simplify, flat, and reverse, there is another one, reparameterize. If you click on this icon, it will immediately reparameterize the domain from 0 to 1. It doesn't care about the aspect ratio. What it was doesn't matter. It takes all the numbers and shrunk them to the values of 0 to 1. All right? What will happen next? If this one is 0 to 1 and this one is 0 to 1, it takes all the numbers and map them accordingly from 0 to 1, effectively stretching your pattern from square to whatever shape of a surface you have. In my case, it is a rectangle, right? And as you can see, it's squared. However, there is a catch. If you look closer, you will notice that it goes to the end here, to the end here, to the end here, but not here. Interesting. Where is the error? Well, actually, there are no error. If I'll go in and I will just remove just lower the amount of division. So this is a flat top, so I'll change the x direction, like for example, 19. Here we go. It's now perfectly matching. Now we need to understand what the hell. So let me go back 20 by 20 and we'll look at the pattern. So I will hide this for now temporarily. I will turn my original centered grid and I will turn on the original unsorted grid. This one. This one was the base. Then we weave it, removed, cleaned it, and we will get this one. Let me just construct the polylines here so it will be visible. Here they are. Look at this. So the grid was from 0 to 1. We have 20 divisions, so on and so forth. You see that it doesn't go to an end. Why? Well, let's try to count. Like we only have in our grid only fully assembled hexagons. So the hexagons which has 6 points. If we will start weaving, we don't have enough points. And we literally cut them off. We said, leave me only the ones which have all 6 points. And as you can see, this column completely just misses because you can't construct hexagons here, right? But if I will change the amount of divisions, oh, now all of them are in effect, right? All of them, we don't have leftovers. And here we leftovers again. And let's say here again, and here we don't have it. Same here, let's switch from flat top to, let's say, pointy top, right? A problem persists, but in the different direction. Now this one is not in use, right? Well, let's shift it a little bit, and now it works. So basically, because the nature of a hexagons, they are a staggered pattern, there always will be a situations, or some, not always, but sometimes there will be a situations where not all the points are in use, all the edge points are in use, right? Just not enough points. And that's why when we look back to our example here, this is the pointy. Oh, this is a good example. I switched that to the pointy top. You're gonna see that now this one is not go to the end. Well, now it will, right? Let's go back to the flat top here, right? Let's shrunk it on one. Now it works. So can I solve it automatically? Well, the answer is I can, but for that I need to reparameterize the numbers. So right now here, before mapping, I have the values from, in this case, from 0 to 1. In this case, not from 0 to 1. It was originally from 0 to 1. This one is smaller. It was like from 0 to 0.95 or something like that, right? And I will take 0.95 and map it to 0 to 1. And you will get the point which basically it is slightly off. If you add or remove the division, it immediately will snap back and perfectly match the edges. So if I will take these values and reparameterize the domain from 0 to 1, and we will do that, by the way, but not now, we actually can mitigate the problem. However, there is another issue, and this is additional control points. You're going to see, if you remember, I can bring up additional elements to my grid in one direction and another direction, and they fall off the grid because they are beyond the values of 0 to 1. And that's deliberate. You probably don't know why do we need this, but trust me, we need that very badly. And if I will and reparameterize this domain from 0 to 1, I will not have this effect. They will all shrunk to 0 to 1. They will perfectly match the edges, but they will not have an ability to get the overflow. I, of course, can battle that as well, but honestly, because we have the mode, this one, which operates through the divisions, the most natural way when it comes to the stretch is just manually shift the value. And that will be most organic and logical way when it comes to the stretching of isotropic, which of course already doesn't have the proper proportion type of hexagons, right? So instead of trying to reparameterize that, and once again, we will be reparameterizing, but later, not here. But for this, I will actually let it go. And I don't want to change that, right? So hide this one, go back to our original, hide this, look here. Let me quickly fix the error, like this, whoop, and it's perfectly matched. And it actually happens all the time. So if you think that this is a happy accident, it's not a happy accident. It doesn't matter how divisions you have. If it's not matching, you just shift the divisions, or X and Y. That simple as that. So I'll put it back in, so let it be 20 by 20. And we already figured out that it works on both on flat top and the pointy top. So no issues here, works as intended. Right. These out of the way, let's now think about the other modes. So when we are still in isotropic pointy top or isotropic flat top, I can propose another way of mapping. And another way of mapping is not stretching. So what if instead of a stretching, we take our original grid, let me just kind of turn it on, take my original grid and give an ability to take it, toss it to the middle here where the center of the surface is, and then use a factor to make it bigger or smaller. That's really, really important for things to come. It's a really, really important mode, which saves the aspect ratio or the ability to control the aspect ratio, rotate the element. We can rotate it right here as well, of course. Let me just kind of show you that. It still rotates, but as you can see, it stretches, and because it's stretch, when you start to angle, it just skews and bends. I mean, this is a shitty solution. If we want to rotate something, right? It will be actually beneficial if we start from the center, scale it, and then rotate. Then we'll have a much better result and we will maintain the current proportions which we have, right? How are we going to do this mode and how we make it? Well, if you think about it, it's actually quite easy. You see, we have two domains, U domain and V domain, and here these black lines are actually isoparams. They actually show you the actual domain, right? So this goes from 0 to 20, this goes from 0 to 10 originally. Right now it goes from 0 to 1 and 0 to 1. But if it goes from 0 to 1 and 0 to 1, because we reparameterize that, what's the center will be? 0.5 for both. If I will use this as a 0.5 for both, I will just take these values and just stretch it again for the surface. I don't want that. We already have a stretch mode, it's right there. So for the scale mode, what I need to do is I need to operate with the actual domain. So temporarily right click, turn off the Reparameterize, turn off this mode. Now eventually we will do all the proper switches so that we didn't do it manually. But for now, I will just temporarily use the node called scribble, and I will type here, let's say stretch, like this, oh my god, stretch. Okay, all right, once again, we will do it properly a little bit later. Just remember that we have a stretch, and this stretch works with normalized domain. Now we do another mode which is called scale, and for the scale we actually need the proper aspect ratio or the proper domain, the U and the V, the actual numbers, right? This one is 0 to 20, this one is 0 to 10. What is the center? The center for U will be 10. The center for V will be 5. Well, if we work with this domain, we can reparameterize it the way we want. Let's take this one. It's actually a good one. So we need to find this center dynamically. We don't know, right, what kind of a surface we have. And maybe it's right now it's planar, it's rectangular. It can be skewed and distorted and in 3D and bend and twist and whatever. We need some automation here. We need to find the center, a parametric center. And for that, we need to take our domain and deconstruct it by components to dynamically find a center. And we can do that. If we go to the Math tab under the domain subsection, you're going to see there is quite a lot of options for domains. Constructing one-dimensional domains, bounds, remapping values. We will be using all of that except of probably these two. And for today, what we need to do is we need to take this domain and deconstruct it on components. U mean, U max, V mean, and V max. And I will use this node for that. Deconstruct domain squared, or deconstruct two-dimensional domain, right? Now this is the domain. I can plug the domain like this and see the values, or I can plug the surface straight away. It will give us the same result. Let's look what's inside. So U mean supposed to be 0, U max 20, V mean 0, V max 10, right? Does it make sense? Going back to the domain here. Whoop, whoop. Yes, very much so. Vmax 10, V mean 0, Umax 20, U mean 0. Okay. Now, right from the get-go, in most of the battle scenarios, you're not building surfaces in Rhino. You're importing them from somewhere else. For example, from Alias, or ISM, or CATIA, or whatever, you know? And when it comes to the surfaces, especially surface modeling systems, you can't predict what domain they can throw at you. And oh boy, they can be very creative. And for example, when it comes to the alias, you can get domains like from minus 175 to 0.1, for example, or minus 5 to 100 million gazillion. It's totally possible. So what I mean by that is that you're not sure that the first value is 0. You don't have this confidence. You don't know. You need to automatically, just using basic arithmetics, figure out the actual length and actual center. When you don't know that the first number is 0, it can be some number, it can be positive, it can be negative. How are we going to do that? Very simply, as I said, through arithmetics. So first of all, let's find the center. No, let's actually start the domain. Let's find the delta or the domain for the u, right? Now, it's not u max. Once again, it can be from negative value. So what we're going to do is we'll use the absolute value for that, right? So we will type u minimum like this minus u maximum. And we want an absolute value, ABS. That's the proper syntaxes, right? So this one will be u minimum. This one will be u maximum, like this. U min, u max. Let's look at the result. The result is 20. Makes sense? Yes, makes sense. Let's plug some other numbers just to prove my point. But I believe it's, self-explanatory, but just in case. Let's say minus 20 or minus 10, right? To, let's say, 25 or 23, whatever, right? So from minus 10 to 23, minus 10 to 23. The overall domain from minus 12 to 23 will be 33. Makes sense? Yes. So this is our delta for u domain, or I will call it u length, like this. What's about the v length? Well, same thing. Duplicate, let's change the variables to v min and let's say v max, absolute values, v min minus v max, like that, and it will be v length, right? And it's supposed to be, let's plug the different values, supposed to be 10, and it is 10. Okay, now we have the domains, we calculated the domains of the bounds. What's about the center? How we calculate the center? Well, very simply, we sum them up and divide by 2. So expression, it will be u min plus u max divided by 2. Let's plug that in. So this one will be u min. This one will be u max divided by 2. Bam, bam, result. And the result for the domain of 20, the center will be 10. That's correct. So let's type u center. Let's do the same for the v domain, right? So let's duplicate this. This is v min and v max. Change the variables v min, v max. Now you don't really need to bother with the variables if you know what you're doing. Like when I do my scripts every now and then, I don't care about all of that, right? I did it once, I know how it works, I don't care. But if you're picky and if you're, I actually suggest you to do it the proper way, of course. Don't be like me. So v min plus v max divided by 2, right? This one will be v center, and the v center is 5, 0 to 5, right? This is 5. So v center, v length, and u center. We have everything. Let's align that like this. Let's just align it to the right, like this. Right? Cool. All right. Let me actually now move it to the right somewhere here. So let's connect. Let's do it like this. Now we'll organize things a little bit later, just like really quickly. I don't really like a really long angled wires. Where's my mouse? Oh, okay, here it is. So now we have information about the domain. Now what we need to do is we need to take every point, right? And once again, it's on the center. Remember, with the stretch, we move it to the right on positive x and positive y. But for the scale, we don't need to do that. It's already in the proper position. It's in the center, right? This is the center, and this is the center. So if I will take all the points from this grid and put it on the center, basically adding the components, so this one plus the center, it will go with the negative value and the positive value. It will be on the center, right? So what is the center? We have two centers, U center and the V center. So we need two calculations for X component and for Y component, right? So we will go in, we will, let me just bring another, no, I'll probably use the same component here. We'll figure out how to organize everything later. So let me plug that in a little bit here. This one here, expression. So the X component plus the center multiplied by factor. Where is the factor? So if we will take the point and sum with the point on the center, and we know U center and V center, we will get the same size here. If we need to expand that, what we need to do? Multiply that by some number. And this number is a factor. A factor of 1, same size, factor of 2, twice the size, factor 0.5, twice, half the size, and so on and so forth, right? So let's use expression and type U center plus X component over point multiplied by F. X, our coordinate, F will be a factor. So X, now this one will be F, and this one will be U center, and the output will be X, right? Okay, so X component is here, factor, let's say 20, I will type F as a factor, stands for factor, right, like this. Let me just set it back to 1 probably by default, plug it here. What's about the U center? U center is this one, plug that in. This is component X. Let's quickly do the component Y, Ctrl-C, Ctrl-V. This one will be Y, the factor, and the factor will be the same. The U center will switch to V center, go in. So this is a V center and a Y value like this. Let's reconnect. It will be Y, factor is the same, and the V center instead of a U center. Right click, Y. All right, we have two values here. Let's construct a point. Construct point X and Y, and I made a mistake. Where I made a mistake? V center, U center. Oh no, I didn't make a mistake. I didn't plug it. Okay, so yeah, here it is. So as you're gonna see, when we map it to the surface, it's now in the center. And if I will increase the factor, it will grow, right? And it grows with the same aspect ratio as our original grid was, right? And I can easily change that by, I don't know, maybe adding additional rows, right? Or maybe changing the components. That's up to me. And on top of that, of course, I can rotate that. And as you can see, it doesn't really squash and changes the aspect ratio, because when it's stretched, it effectively stretched the aspect ratio. Here it's not stretching, it takes what it is. So when you rotate that, it perfectly maps with the current positions, right? Very useful, because now I can go in and just extend that like this, for example, right? And cover my surface. In the future, a collection of surfaces with the defined defined values, right? And again, I specify what I'm gonna do. Maybe I wanna get more on X, right? Like this, and then maybe I will, you know, maybe I will just make it more of a look like a hexagon, or maybe in the other direction like this. Who knows? Well, it's up to me, right? So basically, that's the scale. Let me go back to the 0 and let me remove all the additional components here, right? Let's change the factor back to 1. Okay, so let me go in and duplicate that and call it scale. Now, so we addressed two modes, the stretch and the scale. Before we move on, let's actually check how our different mode, the anisotropic modes, behave, because right now we have two different modes for isotropics, right? So isotropic stretch and isotropic scale. Does one of them in its current state works for anisotropic? Well, as the scale is already connected, let's check the scale. So now we will go in and switch to Anisotropic Flat top. You look at that, it's awesome. It's scaled, the proper proportions, it's in the middle, it has a factor, no issues whatsoever. Amazing, perfect, perfect, exactly what I want. Okay, what's about the pointy top? No issues, the same. So scale factor works for anisotropic and isotropic, no problem. What's about the stretch? Let's plug the stretch in and look at the results. And remember, for the stretch, it's supposed to be normalized, right? So reparameterize the domain. It's normalized now, and we are in the anisotropic mode. And right from the get-go, we have issues. So it's stretched. It's going beyond the actual surface, right? For the pointy top and for the flat top as well. So it's not only goes beyond, kind of technically supposed to if you want to maintain the proportions, but we are not maintaining the proportions. It's supposed to be like this, but it's not. What's the problem? The problem with the domain, of course. Now, the original construction when it comes to the anisotropic is very different, right? So this one is elongated in y, this one is elongated on x. And you may imagine that if you want to maintain the same proportions, right, there is only one direction. If you can't really stretch it to the surface. If you stretch it to the surface, it just basically ruins the concept of anisotropness, right? You will lose the proportions. What if you want to maintain the proportions but at the same time stretch the surface? Well, that means that you need to pick the direction. You either stretch in one direction and the other one will follow based on your aspect ratio, or so in one and the other one follow, or vice versa. So if you stretch in U direction, we're supposed to follow with a specific ratio. If you align to U, so it's supposed to go to the edges of this in this direction, then the V direction is supposed to be free and supposed to follow the whatever scale factor you have. Right now, the stretch doesn't give us this capability. Stretch tries to stretch in all directions. And just already because of that, it will not work properly. So how are we going to do that? How we make these anisotropic pointy top and flat top useful? Well, we construct ourselves a different method in which we specify in what direction we want to stretch and give the ability to stretch in other direction properly, maintain the proper aspect ratio. And for that, of course, we need to have the proper domain, because when domain goes from 0 to 1, it doesn't have aspect ratio. There's nothing for me to work with. So I will go in, I will disconnect the stretch. I will go in, I will remove Reparameterize. We will once again get back to our original 0 to 20 and 0 to 10 domain, and then think about it. Now, if I will turn on the scale for now and look at this, you will notice that we have a factor. Center plus component multiplied by factor. Factor is a manual switch, right? But we know that the distance is 20. So if I will go in and increase the value to 20, let me just kind of change the proper size so it's not 20, it's 19. You will see that it actually does exactly what we want. So in this mode, the anisotropic flat top works perfectly. It's just this number we set dynamically. Well, it looks like that at least. It's a little bit more complex than that, but let's try and construct this mode, and we call it, let's say, U anisotropic. How about that? U anisotropic. And we construct this mode using our concept of scale, but we will do this dynamically and then see where it leads us. So I will deconstruct this, right? I'm still with not reparameterized domain 0 to 20, 0 to 10, and I will start mapping. Now we are in the flat top mode for now, and let's try to construct the solution. So expression. Now we already know all the components. So we have a component x that will be our x component right here. What next we need to do? We of course need to find the center. So we plug this onto the center and then stretch it with the same factor as the length. What is the length? Here it is. We already have it. It is 20 in our case. So if we'll stretch here, we're supposed to have the proper value. So take this one, align it to the center, multiply, but instead of a factor, which is manual, we will take the factor from the length, right? And because the values are normalized, U length become to be a factor. Exactly. That's why we actually did it in the first place. It's very useful. I hope now you understand the benefit. So we go in and we'll type U center plus X multiplied by U length, right? Okay, U center. So let's type U center, right? Set another one, and this one will be U length. Actually, I believe quite although but U length comes first, so this one will be U length. Now I'm just changing the order because otherwise they will go like crisscross. I don't like that. So this one will be U center. I'm talking about the wires themselves. Okay, let's connect. We go X to X, U length to the U length, and U center to the U center. We get ourselves the number. This one will be X. Okay, what's about the Y? Now, X, and in our case, will be U direction. What's about the Y? How much we need to increase the Y so that with the U direction fully covered, the Y followed with the proper aspect ratio? What is the factor? The answer is the same as U length. When we take the, we basically multiplied X on some number, which means that we multiply the Y on the same number, right? Exactly. So let me just duplicate that. This one will be the Y component. It will be the U length and the V center. U length is our factor, our multiplier, but the center will be different. This center is 10, right, for U, and for the V, the center will be 5, right? So we go in U center, it will be V center on X on U length. Like this, right? Where is the mistake? Oh yeah, of course. So first of all, it's not X, it's Y, right? Y component. All right, right click, Y. Let's connect and let's see where we go, what we have. So construct point, X component, Y component. Let's plug that in. And I made a mistake. Oh yeah, of course, this is the Y component. I'm sorry. Bam. All right, now we have quite a lot of things here, but here we go. And you're gonna see that, yes, indeed, it's stretched properly. However, we have a problem of orientation, and that's probably my mistake. Let's look closer. U length on U center, right? This is correct. This one, U length on, of course, V center. Right there, okay. So misclicked. Now it's perfectly aligned. So we stretch it on U and we followed because the factor U length was the same. Cool. Okay, so this is the stretch of the flat top on U direction where V is following. How about the V direction? What if we will take the same flat top but try to align it to the V, right? Well, let's look at the formulas here, and I believe that first thing we should think about is like, well, it's actually the same. The only difference is that what was the U length, right? Multiplier supposed to be the V length multiplier, right? Well, let's try it out and see what it leads us to. So expression. And once again, X, this one will be V length, right? So now vertical one. And the for X component, it will be the same U center, right? And we will go in and use U center multiplied by, add plus X multiplied by, instead of a U length, we will take the V length, right? V length. So once again, vertical one, right? Makes sense? Well, not quite, but, what am I doing? U length, okay. it will give us an error and a problem, but you will see later why. So u center plus x multiplied by v length. I believe that's correct. So x go to x, v length. Let's not make a mistake again. This is the v length, and the u center is here, right? This is our x. All right, what's about the y? Let's put the expression again. Expression again. Now this one will be y this time, so this is y. This will be the v length again, and this one will be the v center. So this is the y component, right? So v center. Let's go v center plus y multiply by same multiplier, right? V length, v length, right? Make sense? Let's say that that will be y, and I will use the y component, the v length, and the v center. Okay, so we have x and y. Let's try construct point x and y, and then plug that in. All right. Look at that. So we have an issue, isn't it? So the aspect ratio is correct. So we actually, yeah, we kind of halfway there. But as you're going to see, the actual u direction, or the u values, is much bigger than the actual surface. I remind you that in this mode, when I said that the first one we stretched on u, right? And it was from border to border. And then the v direction just followed. It was bigger, but it maintains the same proportions, right? Here in this case, we are lining at v, so the whole thing is supposed to be shorter, match to the edges of the surface, and because of that, this space is supposed to be even bigger. So we're kind of halfway there. It has the proper proportions. It kind of tries to shrink, but not enough. But we actually did the same thing. What's the problem? The problem is in the orientation itself, or more specifically, in compensation. Let's look back at our compensations for the flat top. When we have our original grid for the flat top, and that's really important for the flat, because for the pointy top it's different. For the flat top, x stays the same. Y changes on square root of 3. So when we took the original options, the original values of the domains, and stretch in u direction, everything was synced with the original, distribution, right? We extended the u length and used the same multiplier in a v direction. And because the u direction was the original isotropic direction, we never changed that by any square roots. It perfectly matches to the ends, because the values was between 0 and 1. But when we decided to align to the v direction, we actually look at the values and we'll see that our grid by default has the y values which are not isotropic. They are not between 0 and 1. They are bigger. On how much? On square root of 3. So when we did the same thing by changing the multiplier on the v direction, it goes beyond on square root of 3. What we need to do? Remove the compensation. But if we remove the compensation, we will lose proportions, right? So we just did this compensation to maintain proportions. Now it just goes beyond, yeah. Well, so what we're gonna do, like, okay, well, let's try to remove the compensation. That was the y direction, which need to remove that. Let's try divided by square root of 3. So we add, multiply by 3, now we divide by 3. Okay, it goes to the edges. Now we lost the proper proportions, right? What we need to do? The x component never had compensation. If we removed compensation from y direction, now we need to add it to the x direction. And what we're gonna do? And in this case, we just divide on the same value, divided by square root of 3. We just flip it in a way, right? It was compensation in one direction. Now, because we are aligning to the different orientation, instead of a u, we orient across the v, it's the same V length multiplier. Now we need the compensation on the different side. And that's why both of them are supposed to be divided by square root of 3. This one had square root of 3 multiplied before, this one doesn't. When we divided this, we removed compensation, and here we actually add compensation. And here we go. Perfectly works. So now we have two different modes, right? This one for U direction, and this one is for the V direction, right? Perfectly matches. Amazing. So what I'm gonna do is I will just take these ones, right? And I will bring probably something else. How can I call it? I will call it flat top UV. So this is the flat top UV. How about, oh, let's just do it like this. Flat top U. And this one will be flat top V. Like that. Okay, last but not least, what's about the pointy top? Yeah, the pointy top will not work here as well. Why? It's vice versa. The pointy top by default has compensation on X direction, meaning on U, not on V. It's different. So we need to do it as well, but with a different compensation distribution, right? So I'll just turn that off, right? We will go in, and now we will take, we go pointy top, pointy top U. All right. Yeah, it looks like a spaghetti goat. We'll fix it later. We'll fix it in the next lesson. So let's just finish distribution. So I will use expression again. I remind you we are in the pointy top. So X component. What's about the X component? X component is already extended, right? So the Y between 0 and 1, this one on square root. So we need compensation right from the get-go. So the U component means that we need a U center. So U center plus X multiplied by U length, right? We go in the U direction. This is our factor divided by a square root of 3. And this is the removing the compensation. It already have compensation, we remove the compensation, right? Ta-da! Let's bring values. So this one will be, which one was U center? Or it was a U length. So this one will be U length. And this one will be U center. Right, so this is X, and that will be output X. Did I bring X and Y here? Yes, I did. So what's about the Y component? Let me quickly bring the Y component. That will be Y component. The center will be here, the V center, right? So the Y component on V, but the multiplier is the same on U direction. So U center plus Y multiplied by U length and divided by square root of 3 as well. This one had compensation, this one doesn't. We removed compensation, we need to add compensation, right? Right. So let's go in, let's bring X component. Let me actually kind of do it like this. Okay, so X component, Y component, right? U length and U length, U center and V center. Okay, so we have a problem here. U length, U length. Oh, okay. Of course. I made a mistake again. Typo again. Okay, drag it down. This one X, this one Y. Well, let's see what we have. So construct point. X component, Y component. Plug that in here. Whoop. Let's take a look. Yeah, exactly what we want. Now, once again, you're gonna see that it just kind of a little bit off on the V direction, like as it's not centered. But remember, there is another grid of points, so I could just add the Y component here. Bam, here we go. So as you're gonna see, we are aligning on U, and it perfectly aligns on U. The proportions are still maintained. If there is anything extra, it goes beyond. Amazing. How about the V direction? Let's do a V direction. And for the v direction, it's actually pretty much the same as the original one was. Why? Because they are perfectly in sync. V direction here by default doesn't have compensation, right? It doesn't have compensation. Meaning that when we align it, we will have the same factor on both. We don't need to compensate anything. So let's go. That was pointy top u. This one will be pointy top v. Expression one last time. X, then we will get the v length and the v center. V length u center, the x component u center, the v length. So let's bring the formula. It will be v center plus x multiplied by why v center, u center plus x multiplied by v length. No compensations, like this, and that will be our x. What's about the y? The y will be y, same v length, but this one will be u, or this one will be v center, right? Oops, v center. Let's go in, and it will be v center plus y multiplied by u length. Once again, multiplier is the same. No compensation this time. The y direction by default is the proper one, has no compensation, right? Let's do the same here. Let's bring it up. So this is x, this is y, v length here, right? U center here, b length here, b center here. Okay, let's drag that down like this. Let's construct the point. So this one, by the way, is y. So x and y, switch, hide. We have some additional points here. Yes, we do. Yeah, exactly. That's exactly what we want. So as you're gonna see, now it tries to fit on u direction, and the on v direction, and u direction follows, right? So if I will, let's say, like change the value so it will go from the beginning to the end, it's really visible. We maintaining the same, we really try to maintain the same proportions. And by the way, one important note, when you are in anisotropic flat top or an anisotropic pointy top, your actual division is supposed to be identical. Like for example, this is 20 by 20, you don't want to have a spacing, you move two of those, right? You need to maintain the same proportions, and that will work only you have identical values on x and y divisions, right? So, but you're gonna see here that for pointed top v direction, it aligns to the v, and u is follows. It can go over or through the surface or don't go to the edges. It doesn't care. It just follows the proper scale which formed by the correspondent edges of a surface, right? So that's true for v, that's true for u, for pointed top, and for the flat top, right? Right, so now we'll just kind of do it like this. And as you can see, we have quite a few modes: stretch, scale, and then anisotropic flat top and anisotropic pointed top for u and v accordingly. And on top of that, we need to switch the modes here. So it depends. If it is a stretch, then it's supposed to be normalized. If this is not stretched, then it's not supposed to be normalized. So as you can see, there are quite a few of switches we need to add. We will do it in the next lesson. This one already is a little bit too long. So in the next lesson or the next session, we will organize things a little bit better. We will create all the proper switches, so we don't really need to do it manually every single time, and actually look at the next representation of a script. The next ability of our script is, of course, the closed geometry, how the closed geometry actually represents on a surface, because when we did it on flat representation, and I said that in 3D it will look exactly as it's supposed to, and in the next lesson we actually see how all of this construction works. Alright guys, thank you very much for watching, and I will see you in the next one.